elements. So first of all, we recall the definition of a point from a set. Suppose we are given a metric space xt. Then the distance delta from an element x belonging to x to a non-empty subset m of x is defined to be the infimum of all the distances of this point x to the point y bar belonging to m. So first of all, we calculate the distance of x from all the point on this set, and then we find the infimum of the distances of this point x from the point on the set, and that infimum is the distance of a point from a set. If instead of metric space we have a norm space, then this distance is defined as infimum of norm x minus y bar, where y bar belongs to m. Because in norm space metric is defined as in terms of norms, means dxy is equal to norm x minus y. So this definition in norm space is equivalent to this. So delta is equal to infimum norm x minus y bar belonging to m. So it is important to know whether there is a point y belonging to m such that delta is equal to norm x minus y, that is a point y belonging to m is closest to the given x, and if such an element exists, whether this element is unique or not. So this is an existence and uniqueness problem, and this problem is of fundamental importance theoretically as well as in applications point of view. For example, it is useful in a connection with the approximation of function. So we know that the distance of a point from a set is infimum of norm x minus y bar, where y bar belongs to m. And here in this lecture we are concerned about finding a point y on the set M such that y is closest to the given point x. Means we are concerned about finding y such that delta is equal to norm x minus y. So here we see that in this example, if this is the set M, then there is no y belonging to M for which delta is equal to norm x minus y. And in this case, we see that we have a unique y belonging to M such that delta is equal to norm x minus y. And here we have an arc, so we can have infinitely many y's. One point is this, one point is this, one point is this, and there are so many points for which delta is equal to norm x minus y. So this example illustrates that even in very simple case like Euclidean plane r square, there may be no y, there may be precisely one such y, or there may be more than one y satisfying the equality delta equal to norm x minus y. And we may expect that in finite dimensional space will be much more complicated in this respect. For general norm spaces, we may have a y which is unique, we may not have a y, or we may have more than one y's. But for Hilbert spaces, the situation remains relatively simple. This fact is surprising and has various theoretical and practical consequences. It is one of the main reasons why the theory of Hilbert spaces is simpler than that of Banach spaces. So to consider the existence and uniqueness problem for Hilbert spaces, we need two key concepts, segment and convexity. So what is segment? The segment is a line. The segment joining two given elements x and y of a vector space is defined to be set of all z belonging to x, where z is of the form alpha x plus 1 minus alpha y, where alpha is a real number lying between 0 and 1. So in this case, this may be 1z, where alpha is 3 upon 4, 1 minus alpha is 1 upon 4. So 3 upon 4x plus 1 upon 4y. This may be 1z, or alpha equal to 1 upon 2, 1 minus alpha 1 upon 2, this may be 1z, and alpha equal to 1 upon 4, 1 minus alpha equal to 3 upon 4. So these points are of the form alpha x plus 1 minus alpha y, where alpha lies between 0 and 1 and alpha is a real number. So the segment joining two elements x and y of a vector space X is defined to be the set of all z belonging to X of the form z equal to alpha x plus 1 minus alpha y. Now a subset M of X is said to be convex if for every xy belonging to M, the segment joining x and y is contained in M. Like in this example, also every subspace Y of X is convex and intersection of convex sets is convex. Now we will prove one result. Suppose X is an inner product space and M not equal to phi, means M is non-empty convex subset of a complete inner product space X. In this case, the metric induced by inner product. Then every given X belonging to X, there exists unique Y belonging to M such that delta is equal to infimum of norm X minus Y bar, where Y bar belongs to M, or we can write it as norm X minus Y. So in this case, we have to find that there exists unique Y belonging to M, which satisfies delta equal to norm X minus Y or infimum of norm X minus Y bar, where Y bar belongs to M. So first of all, we will prove the existence part, then we will prove the uniqueness part. So suppose there is a sequence Yn in M such that delta n tends to delta and delta n is equal to norm X minus Yn. First of all, we will show that this sequence Yn is a Cauchy sequence. Suppose we write Yn minus x equal to Vn. We know that norm X minus Yn is equal to norm Yn minus x. So I have written Yn minus x equal to Vn. So it means norm Vn is equal to norm of delta n. As I told you that norm X minus Yn is same as norm Yn minus x. So we can write norm Vn equal to norm delta n. So norm Vn plus norm Vn Vm is equal to Vn is Yn minus x. So Yn minus x, Vm is Ym minus x. So Ym minus x. So Vn plus Vm means Yn minus x plus Ym minus x. So Yn plus Ym minus 2x. If we take 2 common, we can write it as 1 upon 2 Yn plus Ym minus x. I have taken this 2 outside and written 1 upon 2 here. Because M is convex and this 1 upon 2 Yn plus Ym belongs to M, therefore this half Yn minus Ym minus x norm of this distance is greater than delta, and we have 2 here, so this is this 2. So by convexity and by the definition of infimum, norm of half Yn plus Ym minus x is greater than delta. This is by definition, by this definition. Because if Yn is in M, then norm X minus Yn is equal to delta n. So further we have Yn minus Ym. So Yn minus Ym means Yn is Vn plus x. So Vn plus x, Ym is Vm plus x. So Vm plus x, so Yn minus Ym. Vn plus x minus Vm plus x. So x will cancel out. So we are left with Vn minus Vm. So by parallelogram equality, norm Yn minus Yn whole square is equal to norm Vn minus Vm whole square. So we know that parallelogram equality is norm x plus y whole square plus norm x minus y whole square equal to 2 times norm x whole square plus norm y square. So from here, if we shift this term to right side, norm x minus y whole square is equal to 2 times norm x square plus norm y square, and this will come this side, so minus norm x plus y whole square. So if we apply parallelogram equality here, so this is minus Vn plus Vm whole square plus 2 norm Vn square plus Vm square. We have applied this. Now Vn plus Vm, norm Vn plus Vm is greater than or equal to 2 delta. If we apply by minus on both sides, greater than or equal to will become less than or equal to, because when we multiply by minus sign, the inequality will change. So because we have minus here norm Vn plus Vm is greater than or equal to 2 delta. So here we have minus, so this is less than or equal to minus 2 delta whole square. Norm Vn is delta n square, norm Vm is delta m square. So as because delta n tends to delta, so it tends to minus 4 delta square plus 2 delta square plus delta square, means it tends to 0. It means norm Yn minus Ym is equal to whole square equal to 0, because norm cannot be negative, and therefore Yn minus Ym is equal to norm Yn minus Ym equal to 0, and this implies Yn is a Cauchy sequence. Since M is complete, so by definition of completeness, every Cauchy sequence is convergent to a point in M. So it means Yn converges to Y, and this Y belongs to M. So because Y belongs to M, therefore norm x minus y is greater than or equal to delta. Also norm x minus y is less than or equal to norm x minus yn plus norm yn minus y. We have subtracted yn, we have added yn, and we have applied the triangle inequality of norms, because we can write x minus y as x minus yn plus yn minus y. So apply the triangle inequality, norm x minus less than or equal to norm x minus yn plus norm yn minus y. Now norm x minus yn is equal to delta n, and norm yn tends to y. So because delta n also tends to delta and yn tends to y, means yn minus y tends to 0. So norm yn minus y tends to 0. So it tends to delta. So it means norm x minus y is equal to delta. Because here we have shown that norm x minus y is greater than or equal to delta. Here we have shown norm minus x minus y is less than or equal to delta. So by these two inequalities, norm x minus y is equal to delta. Now the uniqueness part. Suppose y belongs to M and also y naught belongs to M, and both satisfy the equality norm x minus y equal to delta. It means norm x minus y equal to delta and norm x minus y naught equal to delta. Now we will show that y is equal to y naught. So if we apply parallelogram equality, then norm y minus y naught whole square is equal to y minus x subtracted x minus y naught minus x, minus minus plus, so we have subtracted x and we have added x. So now apply the parallelogram equality. it will be twice of norm y minus x whole square, twice of norm y naught minus x whole square, minus norm y minus x plus y naught minus x whole square. Because this is x minus y, so shift this to this side. 2 twice norm x square plus norm y square minus norm x plus y whole square. In place of x we have y minus x, in place of y we have y naught minus x. So it is twice norm x square twice norm y square minus norm x plus norm y. So in place of y we have y minus x, in place of x we have y minus x, in place of y we have y naught minus x. So we have made use of parallelogram equality here. It is nothing but delta, so it is 2 delta square, it is also delta, 2 delta square, and this is y plus y naught minus 2x. So if we take 2 common, so outside it will be 2 square, so inside we have 1 by 2 y plus y naught minus 2x, so x, because 2 I have taken outside. You can clearly check this is y plus y naught minus 2x. Take 2 outside, outside it will be 2 square because we have square term here. So 1 by 2 y plus y naught minus x square. But this belongs to M. Half y minus half y plus y naught belongs to M, and M is given to be convex. It means this distance is greater than or equal to delta by definition. So it implies that norm y minus y naught whole square is less than or equal to 2 delta square, 2 delta square, and this is 2 square means 4, and it is again because here we have minus, so it will be less than minus delta square, because when we multiply by minus sign, then greater than will become less than. So minus half y plus y naught minus x is less than or equal to minus delta. So it is 2 delta square minus 4 delta square. So it is equal to 0. So because norm y minus y naught is whole square is less than or equal to 0, but norm is always positive, so we must have y naught y minus y naught equal to 0, or y equal to y naught, or y naught equal to y. One more result: a closed convex subset of a Hilbert space contains a unique element of smallest norm. Suppose delta is equal to infimum of norm x, where x belongs to A. The steps of this theorem are almost similar to the previous one. Because x and y belongs to A, then 1 by 2 x plus y also belongs to A, because A is given to be convex subset of a Hilbert space H. So it means delta is less than or equal to half x plus y, or 2 delta is less than or equal to norm x plus y. So by the parallelogram equality, norm x minus y whole square is equal to 2 norm x plus y, norm x square plus norm y square minus norm x plus y whole square. So it is because 2 delta is less than or equal to norm x plus y, so if we multiply by minus, sign minus 2 delta will be greater than or equal to minus x plus y, or we can say minus x plus y, norm minus norm x minus x plus y is less than or equal to minus 2 delta. So here we have square term, so 4 delta square. So we have proved that norm x minus y whole square is less than or equal to 2 norm x square plus norm y square minus 4 delta square. Suppose yn is a sequence in A. for which norm yn tends to delta. So as n and m tends to infinity, norm yn minus ym is less than or equal to norm yn square plus norm ym square minus 4 delta square. We have made use of this inequality. In place of x we have yn, in place of y we have yn. So it is 2 x yn ym minus 4 delta square. But yn tends to delta, ym tends to delta, so delta square plus delta square, 2 delta square into 2, 4 delta square, so it tends to 0 as n tends to infinity. It means yn is a Cauchy sequence. But we know that Hilbert space is complete, so there exists y belonging to x for which yn tends to y. Also, because A is given to be closed, therefore y belongs to A. Closed set contain all its limit point. So norm y is equal to limit norm yn. So called closed convex subset of a Hilbert space contains a element of smallest norm. Now the uniqueness part. Suppose we have two elements of smallest norm. Norm x is equal to delta and norm y also equal to delta. So if you make use of this inequality, then norm x minus y whole square is less than or equal to 4 delta square minus 4 delta square, because norm x is delta, norm y is also delta. So delta square plus delta square 2 delta square into 2, 4 delta square minus 4 delta square equal to 0. But norm cannot be negative, so norm x minus y equal to 0 means x minus y equal to 0 or x equal to y. So closed convex subset of a Hilbert space contains a unique element of smallest norm. The element is the element which exists is unique. Now one more result. Let M be a complete subspace of subspace let M be a complete subspace of y, I think it is of y, and x belongs to x is fixed. Then z is equal to x. Then z equal to x minus y is orthogonal to y. Suppose this lemma is false, means in that case z is not orthogonal to y. If z is not orthogonal to y, in that case z orthogonal to y is false, and we would have y1 belonging to y such that norm z minus modulus of z minus inner product of z and y1 is equal to b. Clearly yn cannot be 0. If yn is 0, then inner product of z and y1 will be 0. Also for any scalar a, norm z minus a y1 whole square is equal to inner product of z minus a1 with z minus a y1, because we know that norm x square is equal to inner product of x with x. So norm x is equal to square root of inner product of x with x. Because we have square here, so we have not written square root part here. So norm z minus a1 whole square is equal to inner product of z minus a1 with z minus a1. If we simplify this, we get inner product of z with z minus, because a is on the right side, a bar inner product of z with y1, then this with this, minus, it is on the left side, minus a inner product of y1 with z, then this with this, a bar inner product of y1 with y1. I have taken a common, so here a bar inner product of y1 with y. So you know how to simplify this part, how to calculate the inner product. So this is inner product of z with z minus a bar inner product of z with y1 minus a inner product of y1 with z, and it was a bar inner product of y1 with y1. If we substitute a bar equal to b bar upon inner product of y1 with y1, then in that case this will be inner product of z with z, and this is minus a bar, and inner product of z with y1 is b. This we have already taken. So inner a bar into b minus a. This is inner product of y1 with z. It is z with y1. So I have written b bar here. Conjugate. Minus a bar inner product of y1 with y1. If we take a bar equal to b bar upon inner product of y1 with y1, then in that case it will be b bar upon inner product of y1 with y1. If we cancel inner product of y1 with y1 in the numerator and denominator, then we are left with b bar minus b bar. So this term will be 0, and we are left with inner product of z with z minus, because a bar is b bar upon inner product of y1 with y1, here it will be b bar upon inner product of y1 and y1. If we substitute a bar equal to b bar upon inner product of y1 and y1, this term will be 0, and we are left with inner product of z with z minus b bar upon inner product of y1 and y1. So in that case, if we take norms are equal to delta, norm x minus y equal to delta, because z is equal to x minus y, then this equation norm z minus a1 y whole square is equal to norm z is norm z square minus b bar becomes modulus of b bar, modulus of b whole square upon norm y1, this will be less than delta square, because norm z square minus some term, it will be less than delta square because norm z is delta. But this is impossible. Why? Because z minus a1 is equal to x minus y2 if we take y2 equal to y plus a1. So it means norm of z minus ay1 is greater than equal to delta, because z minus a1 is equal to x minus y2. In that case, norm z minus ay1 will be greater than equal to delta by the definition of delta, because norm x minus y is equal to delta. So here this part is not possible. So it means our supposition that z is not perpendicular to y is not true. So it means we can have z which is equal to x minus y orthogonal to y. So z is orthogonal to y. Now one more result. If T is a operator on a Hilbert space H, then inner product of Tx with x is equal to 0 for every x belonging to H if and only if T equal to 0. Suppose inner product of Tx with x is 0. Suppose x and y belongs to H, it means x plus y also belongs to H. So inner product of t x plus y with x plus y is equal to 0. From here, because it is given to us, in place of x we have x plus y. Because t is linear, so t of x plus y is equal to tx plus ty. So if we simplify it, it will be inner product of tx with x, inner product of tx with y, inner product of ty with x, inner product of ty with y equal to 0. It is inner product of tx with x is 0, tx plus x plus inner product of tx plus y plus inner product of ty plus x plus inner product of ty and y. But inner product of tx and x is given to be 0 if x belongs to H. If y belongs to H, inner product of ty with y will be 0. So this term is 0, this term is 0. So we are left with inner product of tx with y plus inner product of ty with x equal to 0. If instead of y we write iota y, then inner product of tx with iota y will be minus iota tx with inner product of tx with y, because iota is on the right side. If we write iota here, inner product of t iota y with x is equal to iota inner product of ty with x. If we divide by minus iota, it will be inner product of tx with y minus inner product of ty with x equal to 0. If we add this, if we add this equality and this equality, then we will get this and this will be twice, and this and this will be cancel out. So we add these twice. Inner product of tx with y is equal to 0, but 2 cannot be 0, so inner product of tx with y equal to 0 for all xy belonging to H. So it means this is possible only if tx equal to 0 or t equal to 0. So we have proved that if inner product of tx and x equal to 0, then the operator t is a 0 operator. Suppose t is a 0 operator, then we will show that inner product of tx and x is 0. If t is a 0 operator, it maps every element of x and h to the 0 vector. It means inner product of tx and x is equal to inner product of 0x into x. 0 into x is 0 operate every vector of every vector to the 0 vector, so it means it is 0. So inner product of 0 and x is 0, since the inner product of 0 vector with any vector is always 0. Thank you.